So we'll continue where we left study class. So I hope just quick review. So classification task as we'll be using the image based classification where the model is start from VG16, 19, then Google Net, Inception Net, ResNet. So ResNet is a focus because it's very important model used for various real-time application as well as developing core application in the medical field as well as other field as well. And then DenseNet, more deeper model, then Inception, ResNet, and then other models which related in the medical field, and then finally LiverNet, 2.x, RenalNet, and so on. And these things already we discussed quickly. So this was the as a traditional way of developing a CAD system which we discussed yesterday. This you also have seen that all the process. So here you see that why that some pre-processing required in case of histopathology images. Same liver organ is scanned by two macroscopy over. So first is called DP70, which is Olympus macroscope. Second is called Filia 2. Same organ is scanned from the two different scanner. So you can see there is a color variations. So if pathologists want to take any diagnostic decision based on these images, their always decision will be wrong, right? So we need to do some sort of color normalization so that the color problem in the macroscopy should be resolved, right? And this you have seen that liver type SCC. This also we have seen yesterday. So we supposed to start from here as a more deeper of the architecture for classification of liver cancer grades from histopathology images. So this also we have seen yesterday as steps for building a deep learning model, right? Quick review: collect data set from the hospital, or if you get some public data set, it is good because already you have benchmark models and already well established data set. Then try to capture the additional data set from your nearby hospital and then get result validated by the radiologist or your histopathologist or ophthalmologist and so on. Then understanding pre-processing data is must. Creating deep learning model, training of deep learning model, testing of deep learning model, performance evaluation. So here precision recall, F1 score, right? All the matrix analysis has to be done of a trained model. And then testing of a model on the new samples. This is very important because unless if you test the model on the new patient data, the model will not be generalizations. And also you need to think about for generalization of a model, try to get a multiple hospital data because the data you are capturing, what other person is capturing, there may be some slight variations. If you take the two hospital data, mix it, train a model, right, and then you test it on this. So the model itself will be having the multiple way of the scanning of data, right? So that will also is other good options will be try to do that as there. So when comes the implementation, so implementation using deep learning, these are the various framework. You can use Keras framework using TensorFlow, and then you can do for only Keras framework using TensorFlow library, PyTorch framework using PyTorch deep learning library. So these are the steps which already some of things is discussed today, but quick see for any binary classification in the sense that whenever you are trying to find out detect the cancerous or non-cancer tumor, right? So in that case while designing or the building model using any library, keep in mind, right, ReLU activations or better than ReLU activations, Leaky ReLU, P ReLU, SeLU, JLU, right? Advanced activations you try to use that. And the last function is binary cross entropy. But apart from the Barry cross entropy, you can use other loss functions. For example, you can use even the variants of this called weighted cross entropy, is there balance cross entropy, and then Dyer's loss can be used, focal loss can be used, right? Loss of max loss functions can be used, right? So, and combination of as well, right? You can do as well, combine loss functions, right? And then, of course, you select one particular optimizer, any one. ADAM is a prefer in all the, for advanced level of research, but you can do for try RADAM or some new ADAM, new the optimizer introduced for the deep learning. And of course, output layer R base keep the sigmoid activation functions, because the sigmoid activation functions here that give you the probability for the 0 class and probability for the 1 class, right? So again, once you get the probability, then again you have to go for the thresholding operation to get the exact class, right? 0 class and 1 class, right? So if probability close to 0, then belongs to the 0 class, and if the probability is close to 1, then that will belongs to the predicted class will be 1. And sometime may happen, it may be false also predictions, right? So that need to be checked, right, by looking that whether what was the ground truth, what is the predicted, is it same or any difference is there. Then in case of multi-class, so again keeping the first and third the constant, only change on the loss functions. So loss functions will be here critical cross entropy as a loss. I mean, this is a standard loss which everybody start using from this loss function, but you can also use focal loss. So focal loss is used for both, for binary classification task as well as for multi-class classification task. Likewise, you can use the loss softmax, right? That also used for the both binary as well as for multi-class classification task, right? Then output layer, again you have to use the softmax activation, right? So in softmax, as I told you, using, but as a additional operations will be doing the call argmax. So argmax will be using, because it give you the probability of the classes, right? So if you have the 10 classes, so that output will be y hat, which will be the 10 probabilities, right? So here it may be some values, so you will get the 10 probabilities, right? Then you need to use the final class. So y underscore class, predicted class will be, that will be arg max of y hat. So what it is it is going to do, it does here, just scan the column wise, and if let's say this column is having the highest probability, then it will take this belongs to this particular position class, right? 0, 1, 2, 3, this is 4, so it will be 4 class predicted, right? So this as a additional operations, right? After getting the y hat, you have to get a specific class label, right? And here just the model which we have designed in the 2021 LeverNet models. So this is a complete, this is general methodology, I would say, right? Now, it is applicable for any kind of cancer grading. It may be liver, it may be kidney, it may be colon, right? Any kind of this. So depend on the classes, it will be changes. As a study I told you, because in the liver cancer grading, we were having the limited number of samples for higher grade. So we try to class subtype 3 be just grade 3 and grade 4, we need to just merge it, right, to train the models, right? And type 1 we were able to get the sufficient sample, type 2 also the sufficient sample, but type 3 and 4 was the problem, so that's why we merge it, make it as a total 4 class classification problem, right? And before going to the deeper architecture, right, need to understand that as a BG16 architecture, then resonate, and then at least, because API, whenever try to use the TensorFlow Lab API, there the already created model is start from the BG16. So you can test also BG16 and then you can go for ResNet and so on, like advanced models, whatever is there as a classification model. So VG16, this model was introduced in 2014 by the Oxford Geometry Group. That's called here Visual Geometry Group. VG stand for Visual Geometry Groups. It's Oxford, the university. And 16 stand for the 16-baited layer architecture, which includes 16 convolution layers plus 13 fully connected layers, FC layer 3. Not so total 13 plus 3. That's combinations, right? So here you see that this is input data image data, which is color. Then here you see that convolution layers, 2 set of convolution, then max pooling, 2 set of convolutions, max pooling, 3 set of convolution layers, then max pooling, 3 set of convolutions, max pooling, 3 set of convolution, and then here again one max pooling, then 1 cross 1. That is converting as a finally one hot. You flatten it, and then 2 fully connected layers will be there. Finally, our last output will be a 1000 nodes, because this particular model is for design, and this was a challenge of ImageNet large scale visual recognition challenge in that was again conducted 2024. It started in 2012. AlexNet was the winner, but in between, like 2012 and 14, the variants of the AlexNet also introduced little bit minor modifications, but this was the one of the, I would say, in 14 was the best model, because this model is having the generalizations in the sense that they are using all the convolution layers, they are using the 3 cross 3 kernels, and max pooling they are using the 2 cross 2 kernel size, and the stride they are making as a wherever convolution stride is 1, right? But AlexNet, what was there? They are using the different stride as well and different kernel size. So that was a major problem. So they make it a streamline the model here. They bend little more deeper, and uniformity they maintain that whenever convolutions means 3 cross 3 kernels will be used. Okay. So whole the VG16 architectures you can split into 2 parts. That's called feature extractor and classification part. So if you see that here, from here to here, right, that's called feature extractor part, and from here to here is called 3 layer 3. That will be called as a classification part, right? So in feature extractor you can see the very clearly in this slides. Input data is 224, comma 2 cross 224, cross 3 color image, and then doing the 2D convolution, right, with the kernel size of 3 cross 3, right? And you are getting, and here also using the zero padding, right? Study I told you concept of zero padding, right? So zero padding, so after convol we are getting the 224 into 64. 64 means at this particular layer they were using the 64 number of filters to do a 2D convolution operations, right? That means this particular layer 64 different feature were extracted, right? And since there are 2 consecutive convolution layers, whenever is a consecutive convolution layers you have to use, make sure the number of filter remains same, number of kernels should be same, don't change that. Okay, so again 3 cross 3 convolution layers, again the number of filter remain the same, right? And then max pooling. So max pooling, as told you, the idea is just do the subsampling, right? So earlier the size whatever was there 224 cross 224 divided by 2 become 112 cross 112 cross 64, right? So this we got as here this first step. Then again 2 set of convolutions. Now you see here using 128 number of filters, right? Kernel size remains same 3 cross 3, but number of filter is increased 128 120 because these are 2 consecutive convolutions layer, right? And then max pooling. Then here 3 consecutive convolution layers. So here 256 256 2, each layer convolution layers they are using the 256 cross 256. That means they are extracting the each layer 256 different feature values. Okay, then again this will continue the same pattern here, right? So finally you see the 256, 512 and 512. These are having maximum 512 cross 512 kernel number of filters. Don't go beyond that. And this was required because this was trained on the, that imaginary data set which were having the millions of the images, right? So that's very high volume data, right? But if you are trying to same model for your project work, right, your task, you should follow the structure. You need not to follow the same number of the like this filters. This should be get fine tuned based on your problem statement, right? You can start maybe 32 or 16, right now, and then you can slowly increase 16, 32, 64, 128, like that you can go, right? And may not be even this 16 layer architecture may not be also needed. You can customize it. You can make it as a 13 VG16 also, right? VG16 is a like unique thing is that uniform pattern, right? Conclusion 3 cross 3, right? And the stride is 1 fix, right? So you can do the same things, right? So I hope this clear feature extractor part. This is the same things was there in feature extractor. All the things a little in bigger way you can see that, and each layer you can calculate the width and height of the convolve feature map by using the formula yesterday what we discussed it. Okay, and then next is the fully connected layers. So fully connected layers here. So first need to do flatten, right? To do the flatten yesterday I told you very simple concept. 2D matrix need to convert as a column vector because this fully connected layers is nothing, it's a ANN, artificial neural network, right? Which always accept data in the column vector form, right? So we need to do flatten operation. Then after that dense layer. So dense layer here using 4096. That means this much node required only for imaginary data set. If you are using your own data set, this much node not enough, not needed. You can use maybe 512, that will be enough, or even the 256 nodes, right? Because this much feature going to connect this many nodes, like see that, okay? And then dropout. So dropout basically used to, during the training what happened, and it may be what I say that dropout always use a percentage, right? So it may be like 25% or maybe 50%, right? So what happened dropout, if you are using 50%, so 50% node, if you write drop point 0.50, means during the training randomly 50% nodes become inactive. Out of how many? Out of 4096. If you say 0.25, means 25% of the 406 nodes that become inactive right now. So dropout is necessary to overcome the limitation of overfitting problems, right? So keep in mind that the role of the dropout here. Then next here again the dense layer means nothing's your NN part, right? And here again the same number of nodes used. Then again dropout, and then last you see dense layer, which is nothing the softmax, right? So softmax with the 1000, so you will get the on imaginary data set having the 1000 classes of that. Okay, so this is just as a the concept of the this VG16 architecture. It's very important. When you start learning, so start from the LeanNet 5, LexNet, and then VG16, go gradually. So increase the complexity gradually. And then coming to the VG19 model. So VG19 is nothing, is an extension of the VG16 only. Here 16 convolution layer and 3 fully connected layers, right? So that total having the 19 weighted layer. I hope that makes sense. Okay, so you can also try VG16, VG19, depend on the data set, whatever you have, your project problem you are working that, right? Then this is called residual network, right? ResNet. ResNet stands for residual network. It's very important and frequently used for many applications. Also now, whenever you do the segmentation task, as an encoder side, it is also used as a like pretain, right? As an encoder, pretain features that are used from the ResNet there also. So it's very important ResNet as far as architecture is concerned. So there are various variants of the ResNet model architectures. That's called ResNet 18, ResNet 34, ResNet 50, ResNet 101, ResNet 152, right? But this is most important, right? Why ResNet 18, 34 are necessary? Because when you start learning, right, you have to create yourself everything, right? So creating 50 layer, it will take more time as a concept is concerned, right now. But creating a 18 layer architecture is easy, right? Like once you created 16 layer architecture, 16-bit layer, you can easily create the 18 layer architectures, will not a problem. 34 also you can create, right, will not a problem, right? 50, you have to spend more time for, creating the model, right? Likewise, 101 you require more times, right? 150 more. So these are the variants are available as far as residual network is concerned, right? And then this is already have ResNet 50 with pretrain also available using the TensorFlow that package, right? You can do on the pretrain means transfer learning, right? You can use on the ImageNet bit also, you can work on that. So this case you see that different challenge. So like it started from the 10, 11, 12 where AlexNet was, right, played a big roles, 8 layer architectures. Then it was the extension of election model that was also included, and then VG16 as a challenge. So in 14 they were the winner, then GoogleNet, then ResNet, right? So ResNet was introduced 2015, right? But they were again the winner of the this IELSVC challenge, right? ImageNet large scale visual recognition challenge. That's called IELSVRC challenge, right? And see that they were having even the smallest parameter as well, right? Now 3.57, right? Where this, if you see that here, right, different layer, 19 layer here also was there, 16 layers, then 22 layers, right? So gradually that layers is increasing, weighted layer, right? But if you also see, the number of parameter is not increasing, right? So that means layer is increasing, but the complexity of the model is not increasing. Performance is increasing. So whenever you as a researcher, if you are trying to design a new model, always keep in mind the model which you are designing should be a light model, less number of parameter, and also that give you the best performance in the benchmark. See, you are doing research in 2015 of 25. So in 25, if you are designing the model, should be better than the model which was designed in 2014, 2024 with the similar task or the same data set, right? So some benchmark data set you need to see which already published, well established, and that you take as a for generalization of the model, and you can create even the new data set. So your model should be giving the best result on the 2 at least data set, minimum 2 nowadays. Otherwise very difficult to get your paper published in a good impact factor journal, right? I hope that's fine. Okay. So let's solve that. It's a very popular models. Let's move on that. So one thing is important in the ResNet called skip connections, right? So skip connection is very important, which play a significant role, and they have 2 important things. Like skip connection used to elevate the issue of the balancing gradient by setting up the alternate shortcut for the gradient to pass through that. I'll show you first, then come back. So this is what is the plain block, right? We call as without skip connections, and this side, right side figure is called residual block. So residual block here, if you see, this case just doing the skip connections, right? More clearly you see here, this is we have input, weighted layer, ReLU activation, then weighted layer HX. So what we will do, the residual block, this input is coming. So from here as a identity block, as a functions, also here adding. So whatever the feature extracted with these layers, we are also adding this as a skip connection. Why we are adding that? Because the model also should learn the unity functions, right? And this higher layer, right, at least it should be as good as the like previous layer. It should not be, give you the worst result, right? That's other reasons, right? So this two things, key point is there in the model, like one, the model help us, skip connection help us to, that elevates the problem of vanishing gradient. Number two, the model also is learning that unity functions as well, right, now with the skip connections, right? So this is the key things, right, of the residual. Because of this residual, that's why model become called residual network as a whole. So this block will be using multiple things, when you design the resonate 18 or 34 or 50, right? So this residual block will be used in multiple times, right? We'll come back more detailed. One thing already you have seen that, so like here you see little more on the refinement of the block. So there is one more concept called batch normalization, right? So batch normalization we call as a pre-activation layer. Always when you say batch normalization, it is nothing, it's a pre-activation layer, in the sense that you all should always use before the activation functions. When designing your model, right, wherever you use in the activation functions, before that you have to put called batch normalization. Why need to use batch normalization? It basically reduces the covariant shift internal, right? In the sense that internal covariate will be there during the training models based on the mean and variance steps. There is a paper published called batch normalization. You can read in 2015, right? Especially on batch normalizations. But in general, the main objective is to improve the training performance, right? Means if you are using batch normalization, your training time get reduced. That's only the objective of using batch normalization as a layer, right? So here input X, 3x3 convolution layer, batch normalization, ReLU, then again convolutions, then batch normalizations, whatever feature we extracted, then again we doing escape connection, then ReLU activations, finally give this called residual. This is standard, right? What we discussed previously, right? It is with batch normalizations. And one more things we can do, since we are using unity here, right? Little further you can improve the performance by adding what? Instead of unity functions, you can also add 1x1 conversion layers. Okay? So you will see that the performance of the model get further improved. Okay? But this is a standard residual block, right? Now, which is used that. You can also come up with this, or further you can also modify this by using, instead of the standard convolutions, you can use separable convolutions. If your intention is to design light model for object detection task, or you can use the dilated convolutions, right? That will also help you to improve the feature extractions, right? So there are various ways of to modifying the residual block, right? And there are some other concept can be used that, right? So this is because the heart of this was there, right? As a residual in a resonant model, this was the main things, right? That was the, and very lot of citations of this paper got it that. This is nothing that similar to what you have seen that, like as a skip connections and then the convert 2D with batch normalization here. Here there was no batch normalization, only convolutions. You can also put, so in the skip connections, convolve and then batch normalizations, right? That will further improve your training performance, right? And if you see that convolution layer 2D, convolve 2D, batch normalization, ReLU, convolve 2D, batch normalization, ReLU, convolve 2D, batch normalization, and we are adding then applying the ReLU activations, right? If you using here, there is no point of then using there, right? So we are adding here, see here, convolve, batch, both added, and then after that use the ReLU activation functions, right? Keep in mind, don't do mistakes here, right? Always you do after the adding the features. So this is the 2 points I told you as mitigate the problem of Banachek gradient by allowing this alternate shortcut path for gradient to flow as well. And the model also allowed to learn identity function which ensure that higher layer will perform at least as good as the lower layer and not worse, right? This is a key point, right? Always keep in the mind why the skip connection use that, okay? And this skip connections is extensively used, as I told you, as a classification model and also in the segmentation model as a backbone point of view also, right? So ResNet 34, the model, and 34 again means there are total 34 bitted layers. So you see this part, you get the idea. So this is VG19 models, right? And then this is a plain 34 layer architectures, right? So start from here input data and then you get the fully connected layers, average pooling, then fully connected layers, right? Here are 3, but here get changed here. So up to here there is a call 3 cross 3 convolution layers, right? And then average pooling, and then after that dense layer use, right? Now, and this plain layer. Now this is called 34 layer residual network. See that here from here to we are using that. Here 2 consecutive, right? Escape connection used, then 2 consecutive convolution layers, then escape connection like this, like this. This is a standard, 34 layer architecture ResNet right now, okay? Nested up. Here also see that, go back, 1, 2, 3 here using, right? Here how many using? 2 using, right? So you can modify right now, but minimum 2 have to use right now. So here also standard they are using 2 base as a ResNet model right now. Some concept I am telling you, you can, when you doing the project work, doing research, you should have some scope to modify the residual block right now, okay? In between some more concept, there is squeeze and excitation block is there. You can also use that in a skip connection, see that what will happen right now. So you have to look at multiple way for modifying the model. To get paper published, at least 2 novelties should be there in your models, in a high level journals, for example transactions or IEEE journals. Until novelty is not there into architectures, now standard model publishing is very difficult. Unless you have created completely new data set, and that data set is very useful and very unique data set, right? I hope that able to get it idea. This is a ResNet 34. Same way, right, you can create the ResNet 34 model, ResNet 101 and then 152 models also, other variants also can be created that. This is the same things within a vertical way, nothing else, right? So now this summarizes all the variants of the ResNet, right? So layer name here different, output size 18 layers, 34 layer, 50 layer, 101 layer, 52 layer, right? So first convolve laser 112 cross 112, convolve 2, right, which 56 cross 56, right? And this will be common for all the cases. So here type 2 will be common. And then when 2 layers, second convolution layers, 18 layers, 3 cross 3 into C into 2 times, means 2 times use this, right? Then next time third convolution layers, this use again 3 cross 3, 128 filter 2 times use. Then fourth, 14 cross 14 output size will be, and here 3 cross 3, 256, 256 2 times, right? Cross means 2. Same configuration used into 2 times, right? And then 5x means 512 layers here 2 and 2 times use the same models, right? And this having the flops, floating point operations, basically 1.8 to 0.9, 34 layers, this 3 times use, right? 4 times use, 6 times use, 3 times use, this much, that number of the filters, right? If you see 550 layers, 1 into 1 64, 3 cross 64, 1 into 1 256. This configuration is used in the 3 times in the models, right? Then 1 cross 1 120 is, right, 3 cross 3 120 is, 1 cross 1 5 to 4 times used, same blocks, right? Now, so what happens, you can create this block and you can call multiple times. You can just call that, right? Now, residual block. You can create and you can call multiple times with the bearing filters, right? Then 101 layers, you can see that similar way. Then 152 layer residual network architectures you can create, right? So if you know, if you understood this architectures, you can create that. But again, do not waste time for creating models all the time. Once you understand, right, 50 up to 50 models, you try to do something better, right? You design new models, modify other blocks, introduce new feature blocks, and you can come up with the best model right now. Then application of the ResNet model as follows here. You can do handwritten digit recognition, image data set, segmentation task also will be used as a backbone, breast cancer, kidney, all that, like you can do for like binary classification task, you can do multi-class classification tasks like molecular subtype of cancer detections. You can do also use for land-use land cover classification, steel surface, and so on, right? So application is vast of this ResNet model, right? So this is like available as a with the framework as like pre-trained. Keras, as I told you, as a framework front end, back end will be a TensorFlow. You can use as a API, and several pre-trained models on the ImageNet data set. Right, so it's easy to build, need not to for various applications. Whenever you do like computer vision task like object detection or some other, right, where you need not to, especially you should careful in a medical field, right. Apart from the medical field, don't worry, try to use maximize the pre-trained model if available, right. That will be save your time and you can do that, right. But of course again, research means something novel, right now. So you have to come up thinking beyond that as well. So here how to resonate with the Keras framework. Step 1, you have to write code, define identity block to transform the CNN into residual and then build the confusion blocks. Step 2, next build a 50-layer ResNet model by combining both blocks. 3, finally you need to train the model required task, and then Keras framework allow you easily to generate a detailed summary of the models, which you can see that 50 layers are not there, right. So this is a doc, TensorFlow API. If you visit that, you can see that what are the applications are available. How will do that? Base model application.resnet50.resnet50. This is the way you have to do, right? If you are calling a resnet 50, if you are doing VG16, you can write here VG16, right? You can also do DenseNet, you can write whatever model you want to use. That way you need not to code from the scratch, you can use that. I mean, one is called base layer, other is called the top layer, right? So base layer you can retain, right? Top layer you can fine tune, that's right, that's good. So base layer you can retain and top layer you can fine tune, or you can create completely the architectures. If you are doing if you are research scholar, I would suggest you have to create, right, models, because once you create you will learn that right now, okay. And when you creating you will do mistakes also, right. When you corrected mistakes, definitely there will be that happiness will be there in your face, right. Then include underscore top means false, right. That means top layer means feature classification layers I am talking, classification part, right. Classification part, we do not want to standard what is used in the API, right. We want to use ourselves, right. We want to fine tune that, okay. Input false, comma, input, and this here bracket, weights equal to none. Weights equal to none means the model will train from the scratch, right. None means if you say ImageNet means the weight will be, the starting weight will be the ImageNet weight, right. And then after that only fine tuning the top layers here, right. So here everything will be trained from the scratch. Input underscore shape equal to image height, comma image width, comma 3. 3 means that color image, right, okay. And of course, API is everything written, this part is for color image, right? And then, already I told you, this part fine. Then x equal to base underscore model dot output, which is this part you have then. Then x equal to global average pooling 2D. This global average pooling is nothing, it's a kind of flattening operations. This also used, right? This is a faster approach than the flattening, right? Now you can use. Then you can use some kind of dropout. Here is written 0.7 just for understanding, right? Now you can use. And then finally the prediction equal to dense, number of classes, activation equal to softmax, right? And then model equal to model, inputs equal to base underscore model dot inputs, comma outputs equal to predictions this here, right? So if you want to add one more here, right? If you want to add one more dense layer, you can add. That's not a problem, right? Since in the resonate only one dense layer is there, right? Is specific, right? So you have to use standard. If you want to modify, you can do that. That's not a problem because we have flexibility here, right? We are trying to create this part, right? Now we are not using the inbuilt part, right? I hope that makes sense. So here you can do on ImageNet data set, CFAR is a colored image, right? So if you want to do resonate model, you want to implement, always go for the CFAR 10 data set, right? So this is my link actual drive. I mean this may be working always. So other things, if you see that this is like API, if you click there, I'll show in the lab part as, right, all the pre-trained models available are there in the models, right? You can see that, okay? And again this my link. This is a complete classifying on ImageNet classes with the Resonate 50 data set. So here if you see that we are importing everything like TensorFlow.keras.application.resonate import as a Resonate 50, then TensorFlow.keras pre-processing import image .application.resonate pre-processing underscore input import decode predictions, and then import numpy is this, model equal to Resonate 50, weights equal to ImageNet. That means I am going to work on the pre-trained bits right now. I am not training from the scratch because using the ImageNet bit here. Then give the path, right, and then your load the image, you can convert as a array, then expand dimension, then pre-process, then model.predictx, you can do. This is called complete transfer learning, right? We are not doing anything from our side. Everything is ImageNet, ImageNet data task, right now. And these are the like models which are pre-trained available for the, even more available. This was the old slides, right? In 2021, I would say, prepared that time was there. So exception V16, 19, Resonate, Inception V3, Inception Resonate V2, Mobile Net, Dense Net, NAS Net, Mobile V2 and so on, right? So these are the already available baits on the ImageNet baits trained models are available. You can best use of those models for some applications like agriculture applications, doing crop classification. For that case you need not to train, you will not have enough data, right? So you can use these pre-trained models and you can build some solutions for farmer case. So summary about the Resonate as follows here. Resonate is a powerful backbone model that used very frequently in many computer vision tasks. Resonate uses skip connections to add the output from the earlier layer to later layers. This helps mitigate the balance gradient problem. You can also use as a pre-trained Resonate 50 or code it from yourself or in your own private data set, right? It's up to your choice, right? So quick, just 5 minutes more. This is a model which we have designed, already you have seen as well, right? So this model was giving the LiverNet model average test accuracy on KMC data set. This we created 90.93. Average test accuracy on TGCA data set. TGCA is a public data set, right? So this also we created, downloaded and created the data set which giving 97.72. Number of parameter was 7396. And then this complete model, if you see here ASPP block, then here bilinear upsampling here, and then all connecting this here, and then using the different global average pooling, then fully connected batch normalization and so on, then finally able to do that, right? So they, now as far as novelty is not that much level, right, when we were designing, because this was our first task when we were doing in 2021, right? So but later on we felt that the model, the novelty could be improved, the performance can be further enhanced, the complexity can be reduced there, right? Then and this model was nothing extension of this model, right? That was bracelet what was available, but their model was complex, so we had come up with a that simplest model as well. This you can read the paper, this base bracelet model paper you can read and understand later on. This what we propose that. So this is like as a standard conclusions which already I have told you before study also. One concept called 2D atruse convolutions, which called dilate convolutions. So here whatever formula is there, xi plus r dot multiply m comma j plus r dot n w m common. W is a filter or the kernel, and here the input data. So r is basically the rate, different rates, dilation rates. So dilation rate you can depict it in right side if you see here. So here 1 cross 1 conversion filter is 1. So here the rate equal to 2. 2 means that 1, basically the main idea of using the atruse convolution is to improve to increase the field of view, right? FOV, field of view, right? So field of view, how will increase that? By inserting the zeros between the samples here, right? Features here. So if 3 cross 3 kernels, when rate equal to 2, if you see that between 2 feature samples, right, that one gap is created or the zero is filled, right? Now likewise 3, here 2 will be like 6, 5 the zeros will be inserted, right, both x and y directions, and 8 that means 7 that zeros will be inserted between that. So this way increase the field of view, right? And then after all this you need to do calculate all the feature values and then use the 1 cross 1 convolutions. That's how it help us to improve the performance of the model which we design called LiverNet 2. And also use some of the like convolutional block attention modules. Paper is there, you can read this, you can read that more on this. This was the one concept used. This is a data set which we use that. Total we were having basically 141 slides which we got from the KMC, Kasturba Medical College, Mangalore, with a different patient belonging to 3 subtype of the liver: SCC tumor, solid tissue, primary tumor and recurrent tumor. This is called TGCA. TGCA is a public data set. Very libraries there you can download on the US. There are repositories there. And then each size of each pixel is 0.0 to 2.5. 0.25 macron. This is nothing, is resolution basically, right? Resolution of the pixels. Normal slides considered as like this here: subtype 0, primary tumor subtype 1, recurrent tumor type 2. So in TGCA only 3 are there, right? Now, not more that. Then KMC data set which we catered, we got 256 original slides from the different patient, each of having the size of 1920 cross 40, belonging to 4 subtype of liver. And here the resolution was the 3.69 cross macrometers, okay? And this data set has been annotated clinically by pathologist KMC, Mangalore, Mahe, Manipal, Karnataka. 70 slides are used subtype 0, 80 slides for 1, 83 slides for the 2, and 24 slides for the subtype 3, right? And then we also did some random patches of this obtained from the slides, and we did some patches, random 5 patches from the each cases, and created the data set as well. And then we did some training, like also we did 5-bolt cross validation techniques on the both the data set, TGC as well as KMC data set. And the loss we use here, you see that loss functions, right? And also use some regularizations as well here. This L, then loss finally this part. And lambda is used in our experiment is 0.003. Optimizer Adam, learning rate use here 0.001, and also learning rate scheduler also scheme, because it will reduce after like 5 patient, like 5 epochs or 10 epochs. If not increasing, reduce the learning rate further, right? Changes. I mean this that change by factor of this point exponential e to power minus 0.1. The rate will get further reduced that. So this was the result as a class wise 0 to on KMC data set. If you see 0, 1, 2, 3 classes, and these are the ResNet, DenseNet, InceptionNet, IRR CNN model, BreastNet 20, and LiverNet what we proposed. 0.90 was average, and that for the precision, recall, F1 score, IOU, and then accuracy. IOU is not much relevant, but that time we reported, we thought that's not important, but accuracy is most important whenever do classification task. Parameters is if you see that is lower than any other model reported over here, and flops is also lower in our model what we designed. And then this was a TGCA data set also. So model was giving the best result in both the data sets, and this was the confusion matrix for the 3 class case here, and different models here. This was a confusion matrix on KMC data set for the 4 classes, right, of the LiverNet models. This is a computational complexity. You can see that as a graph part. LiverNet model is having the lowest parameter. Then we extended the model by again with the student, right? That's called 2.x model. This model even was much, accuracy has been improved 9.14 on both the data set slightly, and the number of parameters we have 2 variants actually, right? One is even more lighter, 27354 models. So this model was here what is done, this ASPP block get modified, and then here the top plates also get modified a little bit, and this model was again done by the BTech and PhD student as well. So this is my lab here as a first floor is there. Only 2 full-time scholars are there currently. Rest are MTech, BTech are there. And these are the significant project in medical image processing 3 which already completed. These are the glimpses. You can see that outcome of the lab. So this is my GitHub, you can visit and get all the codes are available, right? And also we list called renal automatic grading as well. Also Nature got published in 2023. One more is coming of this year as well, one more scientific report. And this was again extension work, got models in the same data set, grading of kidney cancer. These are the few publications only in histopathology images, what we did it in using the AIML deep learning field. Some more are there going on. This not histopathology, rest all are, see, this is a paper got 2025 got published, work done by MTech student, and one more paper, this also got revision. So he has extended this work, so again under revision it coming very soon right now. So as a future directions, yes, still there is a scope for doing a research in the area of histopathology image processing. You can do segmentation, nuclear segmentation, but you can do instant segmentation rather than doing that part. And of course you can get more data set, prostate Indian data set, nobody is there, you can create that. And breast, I did not find anyone Indian data set which are available, right? Kidney, anyway we have released. Liver, kidney we have done, so if someone wants we can share as well, no problem. But prostate yet to, we are in process of procuring the data from the KMC Mangalore as well. Apart from this, you can go for still hand radiograph, X-ray, mammography, CT, MRI, retinal, fusion, always scope of the further doing some research work, right? May not be doing something like you can develop a product as I told you, right? already some of things, try to come up with the best model, make as a complete base API, or but it would be good to make as a medical product, software product on mobile based device, right? So once a mobile base, of course you have to go for edge devices, right? You have to go for deploy light models, right? So there is a called TensorFlow Lite. So you can, there is a facility, you can convert model, whatever you train model on the that is standard high models, you can convert into TensorFlow Lite. Straightforward, there is a procedures, you can follow that. That Lite model will be running on any embedded devices, edge devices also, right? I hope this is would be useful for you guys, right? Now we'll move on the lab. I'll try to demonstrate one experiment, like how to design deep learning models, right, for classification task, right? Now that I'll take it. How many of already work on that? Can you raise your hand? Okay, so only that takes less number of students have experience. So it will be good. I'll try to do it from the like beginner point of view. Okay, so that you get idea. Yes, Professor.
Could you please comment on the number of parameters, like 200,000 or 500,000?
Yes.
Versus the size of the image coming in 224 by 200.
No, number of parameters depend on the model part, right? So yesterday, if you remember that, I told you we can calculate the number of parameters at each layer, right? Say resonate 50, that means it's 50 weighted layer architectures right now, which that reported was 3.57 million parameters, right? So 3.57 million parameters reported, right? How it's coming, right? That means it's a deep model, right? Each layer, like convolution layers, is have the weights, right? Now parameters. So its parameter is nothing, as I told you, f into the depth of the input image into the number of filter plus the number of filter. So parameter due to the convolution operations and the parameter due to the bias, right?
The system has to learn that many parameters from a few tens of samples of...
No. Samples should be always large. Samples should be large. If you have less samples, then you can go for the graph neural networks. Graph neural network is the right options for when you have a small number of samples, right? So basically you can do graph convolution networks, 2D graph convolution network you can design, right? So what will happen here, the graph neural network that won't accept data as image form. So from the data need to convert into in terms of create as a graph, then give it input to as a model part, right? This is not a very straightforward concept. You have to learn and do that. That could be there, but choice is there, right? Now as a graph convolution networks would be the right options when you have less number of samples. Apart from this, even this you can use liquid neural network, right? Also is for some applications.
When we say number of samples, is it the number of images or the size of the image?
No, number of sample means images. How many number of images you have, right?
Number of pixels doesn't matter.
Number of pixels doesn't matter, right? Number of pixels basically you have to make as a square image. Maybe 224 cross 224 or 256 cross 256, right? That's there. So it won't accept like 1024 cross 1024 data, right? You have to scale down, because why it is there? You will encounter the computational complexity problem, like memory is usage, right? Model won't fit it that in memory. That's why you have to scale down the size, right? 256 or 224, right? Cross 224, right? And so on, right? Depend on that. Or 128 cross 128, depend on the how many samples is there, right? Again, that batch size also matters. Okay, fine. So we'll move to the lab. So lab is located in the adjacent building. This only, the annex on the first floor called DSP lab. So we'll move there. We will try to demonstrate another 40 minutes, right?